So let's talk about Cosets and Lagrange's theorem. So this is the beginning, you might say, of trying to understand the structure of a group by trying to understand what kind of subgroup a group might contain. We will see, for example, the size of a subgroup has to divide the size of the group if the group is finite, etc. And this goes through studying certain subsets of the group given a subgroup called its cosets, left cosets and right cosets. So that's where we begin. The setup is you're given a group G and a subgroup H. Given a group G and a subgroup called H. You give me an element of the group, little a, then I define a subset called A times capital H. It consists of all the elements of the group that look like little a times an element of capital H. So you take all elements of capital H and multiply on the left by little a and collect those guys. That is my A times capital H. It's a subset of G, okay? There's some subset of G. A left coset of H in G means a set that looks like one of these. So a subset C of G is called a left coset of H in G if C is A times H for some A in G. You notice that H is always a coset, a left coset, because H is E times H. If you take all elements of H and multiply on the left by E, you again get the subset H. This is called the trivial coset. Let me give you some example to make this concrete. Let's say G is a cyclic group of order 6 with generator A. Order 6. So this is, 1A up to A to the 5. And it, what is 1? We write E for identity. So E, A, S square up to A to the 5, and A to the 6 is 1. Order 6. Again, I say 1, I mean E. Okay, and H, I need a subgroup, let's say is the subgroup generated by E, A cube. Then what are the cosets? Let's write them out. Well, you have the coset of identity, which is H. Then you have the coset of A times H. Well, maybe I should say the coset containing A. So you have the coset containing identity, which is H. Then you have the coset containing A. What is that? Well, what is H, first of all? H has A cube, and then it has A cube times A cube, which is A cube squared, which is A to the 6, which is identity, which means that the inverse of A cube is A cube. So this is all that H is. It's a two-element subset. So what is A times H? So this is E, A cube. So H is A times E, which is A, and then A times A cube, which is A to the 4th. Okay, then I have the coset of A square, which is A squared times E, which is A square, and A squared times A cube, which is A to the 5. Then I have the coset of A cubed, which is A cubed times E, which is A cube, and then A cubed times A cube, which is A to the 6, which is identity. But aha, look, this is exactly same as H again. So maybe I should put it there. So I don't get a new coset anymore. The coset of A cube is the same as the coset of E. It's the same set. And then I have the coset of A to the 4th, coset containing A to the 4th, pardon me, but that's the same as the coset containing A, you can check. Because if you multiply by A to the 4th, these two guys, you get A to the 4th, and then A to the 7th, which is A again. And then the coset containing A to the 5 is again the coset containing A square. Okay, so there are 3 cosets in this case. Maybe we should make a little table here. The size of H is 2 here. The number of cosets, left cosets, is 3. And the size of the group is 6. Another one, again a group of order 6. Let's take S3, the permutations of 3 letters. And for the subgroup, let me take the subgroup generated by 1, 2, 3. What does that contain? It contains the identity permutation, contains 1, 2, 3, and then contains 1, 2, 3 times 1, 2, 3, which happens to be 1, 3, 2. And then the cube is the identity. So this is a subgroup of order 3. And then I claim H is again a coset, of course. But that's also the coset of 1, 2, 3, you can check. Because when you multiply by 1, 2, 3, you get 1, 2, 3 times E, which is 1, 2, 3. You get 1, 2, 3 times 1, 2, 3, which is 1, 3, 2. And then you get 1, 2, 3 times 1, 3, 2, which is E. So you again get H. And by this similar calculation, the coset containing 1, 3, 2 is also H. And then you have the coset containing the transposition 1, 2. That would contain 1, 2 times E, which is 1, 2. And it would contain 1, 2 times 1, 2, 3, which is either 1, 3 or 1, 2, or 2, 3, I claim. So it would contain these 3 guys. You can check by multiplying. And I claim this is same as the coset containing 1, 3. It's the same as the coset containing 2, 3. So here there are only 2 cosets, this one and that one. This is one coset and this is the other coset. Again, you see these 2 numbers multiply out to the order of the group. So that's going to be part of the theorem. And the other thing you see is that the whole group gets partitioned into these cosets. That's why these numbers multiply out to 6. Each coset has the same size, the size of the subgroup, and they are disjoint. There's nothing common between these 3 sets. And every element of the group is in one of them. The same is true here. There are 2 cosets, they're disjoint, 3 things here, 3 things here, and together they make up the whole group. And this continues even when you go to infinite groups, even though then you cannot count anymore. Let's give some infinite example. So I'm going to take G equals Z, H equals, let's say 3Z, which is multiples of 3. Then the coset of 0, which is the identity in this case. By the way, notice now I'm writing 0 plus H rather than 0 times H, because plus is the group operation. So this AH becomes A plus H. That's really just H, which is all multiples of 3 again. Then you have the coset of 1, which is 1 plus 3Z, which is 1, 4. So you add 1 to all these numbers. And you get that. You have the coset of 2, which is 2, 5, 7, minus 1, sorry, 8, etc. And I claim these are all the distinct cosets. For example, if you take the coset of 7, you're going to add 7 to all the multiples of 3, and what would you get? You'll get 7, 10, 4, right? 7 plus minus 3 is 4, and then 7 plus minus 6 is 1, and minus 2, and 13, etc. So the coset of 7 is exactly the same as the coset of 1. See, this set and this set are the same set. So I don't need to list that as a separate coset anymore. It's already there. And again, in this case, the group and the subgroup both are infinite, so I cannot really count. There are 3 cosets though. But what I still do see is that the group, which are the integers, is a disjoint union of the left cosets. So G is the disjoint union of the cosets, and distinct cosets are disjoint. Maybe one more example. Take G to be the plane with vector addition, and H to be the x-axis. So all points of this form. Then the cosets are the lines parallel to the x-axis I came. This is what I get. And this is easy to see. Here is G. Here is, oops, it shouldn't be so thick. It looks silly. Here is the subgroup, maybe, the x-axis. You give me a, let's say 2, 1. What's the coset of A? I ask. So it's A plus H. Again, the group operation here is called plus, right? So I have to take all the points on the x-axis and add 2, 1 to it. So you're going to get 2, 1 plus x, 0, where x varies over r. And this is just, wait, that doesn't look like 2, 1. More looks like 1, 2, doesn't it? 1, 2. That's going to look like 1 plus x, 2, x in r, which just means that the x coordinate can be anything. Let's say u, and the y coordinate has to be 2. And that gives you this line. So this is A plus H, where you let the x coordinate be anything and the y coordinate is always 2. Yeah. So similarly, you see if you take another point on this line, 3, 2, the coset of that is again going to be the same subset. So the cosets are exactly these parallel lines. And again, the group and the subgroup both are infinite in this case, but you do see that the whole group, meaning the whole plane in this case, is a disjoint union of these parallel lines. And that's going to be the general theorem, which in the particular case when G is finite tells you that the size of the group is equal to the size of the subgroup times the number of cosets. In particular, the size of the subgroup has to be a factor of the size of the group. So a group of size 6 can have a subgroup of order 1, 2, 3, or 6, but no subgroup of order 4. Okay? So the next time we'll see why these cosets form a partition. We need to prove a little lemma which tells us when two elements of the group are in the same coset.